Sometimes it's very hard to take triple integrals using just x, y, z, or just using polar coordinates. Now we're going to introduce cylindrical coordinates and spherical coordinates and actually try to use those new system of coordinates and make it easier for ourselves to calculate triple integrals. Cylindrical coordinates are just generalization, expansion of polar coordinates. So a new coordinates systems. The first one is cylindrical coordinates. And the second one, spherical coordinates. So suppose we have a point in XYZ plane, or a point P in X, Y, and Z plane. We can project that point in XY plane, P, X, Y, Z. We can take a look at the projection of this point in XY plane. So the projection in XY plane gives you point P, X, Y, and of course Z is equal to 0. Very good. So let us convert that into a polar coordinates. This is your R. R is equal to square root of x squared plus y squared, and theta can be written as inverse tangent y over x, and it is actually the angle that the point makes with positive part of x-axis. So now you can rewrite your point in this new coordinate system as P of R cosine theta, R sine theta, or just R theta, and Z stays the same. We call this cylindrical coordinates. When we have cylindrical coordinates for a continuous function on a region, general region like E, the triple integral can be written as f of R cosine theta, R sine theta, and Z. And remember that since it's just expansion of polar coordinates into this new system, dV is now dz r, dr, d theta. Remember that. This is just conversion of dA into polar coordinates, from Cartesian coordinate system into a polar coordinate system. R, dr, d theta. If you're interested in checking the proof of the formula, please get back to the video on polar coordinates, double integrals, and polar coordinates, and you see how we use double Riemann sum and finding those little areas to convert that into R, dr, d theta. Very good. How about spherical coordinates? For spherical coordinates, it's the same process. We say that, hey, we have a point in X, Y, and Z plane. This is just a space. So here you have your point like P. And suppose it's just in this space. P, X, Y, and Z. What are we going to do? We're going to project this point in X, Y plane, the same as before. So this is the projection of P in X, Y plane. So here you have R, theta, and 0 using polar coordinates. And this is your R. Now we're saying that, hey, here you have your point P, and if I find the distance between P and the origin, I can easily calculate that. It's actually square root of x squared plus y squared plus z squared. Let us call it rho. So rho is nothing but the distance between point P and the origin and O. So rho, it's a Greek letter, is square root of x squared plus y squared plus z squared. Well, how about the angle that this point makes with positive side of z-axis? We call this phi. So this angle is phi. By convention, we say that phi must be in between 0 and pi. So phi as the angle is in between 0 and pi. This is just by convention. Very well. So I expect you to ask, what if I want to project this point on z-axis? So let's take a look at this. Let me just up. I'm just projecting this into z-axis and I'm finding the distance between that point and z-axis. Here we go. What is this distance? Row here. Let's sort of keep erasing that. Okay. Let's see what do we have here. First of all, these two line segments are the same, so you're repeating R here. This is your R. Well, sine of phi is equal to R divided by rho. Remember that this is just a right angle, and cosine phi is equal to this length here, which is your z divided by rho. Okay, from the first equation, R is rho sine phi, and from the second equation, z is rho cosine phi. Very well. And remember that your R was defined as square root of x squared plus y squared, and theta was inverse tangent y over x. So x, which was R cosine theta, y was R sine theta, is now can be written R. What is R? Rho sine phi. So rho sine phi cosine theta, and your y, which was R sine theta, is now rho sine phi sine theta. Sine phi sine theta. Let's take a look at these illustrations here. So on the left-hand side, we have cylindrical coordinates. So let us R to be 0. I'm going to change my Z. So when I increase my R, the radius, as you can see, the point which is projected in XY plane gets larger and larger. How will I change my theta in XY plane? As you can see, theta ranges between 0 to 2 pi, and it's just having your nice graph. What if I change my Z? What if I increase my Z? As you can see, your point gets to the larger values of Z. This is your point. So as I'm changing my theta, my point is moving and it creates a shape of a cylinder. This is cylindrical coordinates. Well, how about your spherical coordinates? So this is your rho, the distance between the point and the origin. I'm changing that. So now I'm changing my theta. It means that my point is just rotating. What if I change my phi? Here we go. If you change your phi, as I mentioned before, by convention, it goes up to phi. 0 to pi, your phi ranges between 0 to pi. Spherical coordinates. How about the integral? If I want to use spherical coordinates, my triple integral can be written as triple integral of continuous function f of x, y, and z dv over e can be written as the following. Let me just write it here. I need a little bit more space. X, y, z dv can be written as the triple integral over region E. Of course, I need to change the boundaries. F of x is rho sine phi cosine theta. Y is rho sine phi sine theta. And how about my z? My z is equal to rho cosine phi. How about your dv? It turns out dv is rho squared sine phi. You can write d rho, d phi, d theta. A little bit of a proof for you how we get rho squared sine phi d rho d phi d theta as dv. Very well. So suppose you have x-axis, y-axis, and z-axis in the space. And here you have your shape, your surface in this case. As a spherical wedge, so let us have it this way here. Okay, I'm just trying to make it a little bit nice. Here we go. Okay. A little bit rough here. Suppose you have a wedge here. And your goal is to find the volume of this wedge. So spherical wedge. What is this volume? So suppose we slice the whole thing up and this is just a small spherical wedge, a small portion, a very small part of it, and we want to know what is the volume. So think about it this way. To find the volume, I need to find the length and multiply the base and times it with the height. So what is this length here? What is this length here? And so if you find the base, the rest is easy. Very well. So suppose this is your delta phi. It's a very small change in your phi angle. And here you have an arc, your goal is to find the arc length. So I'm going to write it down here for you. This is your delta phi, and this is your arc. What is this arc length? Remember that in general, if you have a slice of a circle with central angle theta and radius, for example, r, this arc length is equal to r theta. R theta. This is what you learned in pre-calc. Arc length is equal to r theta. Okay, you also know that the distance between the point and the origin is rho. Since you're working with a very small piece here, and suppose you're working with some random points, this is called rho I. Rho I. So this arc length is equal to rho I delta phi. We found this little piece here. Now the rest of it. Delta phi. What is this piece here? For this little piece, let's take a look at it. So if you project this little piece here, let me use a different color for that. In XY plane, I'm just projecting this in XY plane. My goal is to find this little length here, okay? What is this length? At the same time, you know that in XY plane, they have polar coordinates. This is delta theta. What is this length here? This is your, for example, r sub I. So this little length is going to be ri delta theta. But what is your r? Your r is defined as rho sine phi. So this is equal to rho I sine phi delta theta. Very well. We found all the missing elements. This is rho I sine phi delta theta. And we have this little piece here. So this is going to be this. This is going to be this. So this little area is going to be rho I delta phi, rho I sine phi, and delta theta, which is rho I squared delta sine phi, delta phi, and delta theta. Again, you're taking the Riemann sum as those little volumes are getting smaller and smaller. They have the triple integral. So that's how you get rho squared sine phi. Let me see, d phi, d theta, and the d rho. Rho is changing, so d rho, and this is your triple integral.